A crew capsule splashes down off the coast of San Diego. It is Artemis II. 4 astronauts have just returned from lunar distance. Not from the surface. They flew around the moon, looped through deep space, and came back through Earth's atmosphere at nearly 35 times the speed of sound. Recovery teams move in as Orion rocks in the Pacific. It is April 2026. Humans have been to the moon before. The footprints are still there. The descent stages are still there. The tracks, tools, and hardware Apollo left behind are still written into the lunar dust. And it is still hard. That is the problem this video is about. Not whether Apollo happened, it did. Not whether progress is being made, it is. The quieter question is why proving something once does not automatically turn it into something a space program can do again, reliably, decades later. Apollo proved that humans could reach the moon, but it did not prove that reaching the moon had become dependable. It did not prove that the machinery, supply chains, launch systems, landers, training paths, and political commitment would still exist when the next generation needed them. The gap between those two things, between a proof that something is possible and a system that makes it repeatable, is one of the least visible distances in spaceflight, and one of the most important. By the end of this video, you will understand why going back to the moon is still hard, even after Apollo already proved humans could get there. We are going to follow that gap tonight. From the moment Orion comes home, to the moment a lander would have to leave the lunar surface and find its way back. Somewhere along the way, the simple question, why is going back still hard if we already went, becomes a serious one. If you enjoy exploring questions like this with us, subscribing helps the channel keep making more of them. Sharing the video helps even more. Let's begin. The easiest sentence in this story is also the most dangerous one. We already went to the moon. It is short. It is true. It is the sentence that makes everything after Apollo feel like it should be simpler than it is. But listen to what that sentence hides. It hides the launch. It hides the crew systems. It hides the navigation. It hides the return from lunar velocity. It hides the heat shield, the parachutes, the recovery teams, the lander, the suits, the dust, the power, the communications, and the need to do the same thing again without treating every mission as a national emergency. Now picture Artemis II. Not as a headline, not as a recap. Picture it as a test of one layer in a much larger machine. 4 astronauts left Earth, looped around the moon, and came home in Orion. NASA says the spacecraft completed a journey of 694,481 miles, entered the atmosphere at nearly 35 times the speed of sound, and splashed down only a few miles from the target. That is not trivial. That is a major proof, and yet the title question survives. It survives because Artemis II did not land. It did not test a human landing system descending to the lunar South Pole. It did not prove suited surface work in dust. It did not prove power through polar lighting. It did not prove repeated ascent from the moon, rendezvous, transfer, and return across a campaign of missions. So the contradiction is not fake. It is the whole point. Apollo really happened. Artemis II really matters. And going back is still hard because the verb has changed. In 1969, the central question was whether humans could reach the moon at all. Today the question is whether humans can build a path back that is safe enough, understood enough, inspected enough, and repeatable enough to become more than a brilliant exception. We need to separate two ideas that public memory tends to merge. One is possibility, the other is routine capability. Possibility can be proven by a single extraordinary campaign. Routine capability has to survive boring things, production lines, suppliers, procedures, maintenance, verification, training, spares, interfaces, test data, and failure modes that are understood before people ride on them. Think of a mountain. The first successful climb proves the summit can be reached. It does not build a road to the top. It does not guarantee weather windows, rescue systems, supply depots, repeatable routes, or safe access for the next team. Apollo climbed the mountain. Artemis is trying to build the route, the rules, the vehicles, and the habit of returning. That is why this video is not about whether the moon is impossible. It is not about whether Apollo was real. It is not about one program being good or bad. The stronger question is quieter and harder. What exactly did Apollo prove, and what did it leave unproven? Once we answer that, the difficulty of going back becomes much less mysterious and much more interesting. Here is the map. First, we will give Apollo its full weight. Then we will look at what vanished after the sprint ended. Then we will follow the modern chain: crew transport, re-entry, docking, landing, suits, dust, South Pole operations, power, communications, ascent, and the final problem of doing it again. The moon was reached. It was not made routine, and that difference is where the whole story begins. Now, one more distinction matters before we go deeper. A mission can be successful and still leave the next mission difficult. That sounds strange only if we treat success as a final stamp. In real engineering, success is often a measurement. It tells teams what worked, where margins were healthy, where models matched the flight, and where the next proof has to focus. So Artemis II should not be reduced to either celebration or skepticism. It belongs in the middle, a real crude demonstration of the journey around the moon and back, and a reminder that the full moon return problem contains more than the transport capsule. The smarter question is not, did Artemis II solve everything? It is, which part did it prove, and which parts are still waiting for their own flight evidence? Now slow the question down until it becomes exact. When we say go to the moon, we may mean several different things without noticing. We may mean leave Earth. We may mean enter deep space. We may mean pass near the moon. We may mean enter lunar orbit. We may mean land. We may mean step outside. We may mean survive days of work on the surface. We may mean lift off again. We may mean come home. Those are not synonyms. They are separate gates, and each gate has its own evidence. A launch proves ascent under one set of conditions. A flyby proves navigation, crew transport, and return without landing. A landing proves descent and surface contact. A surface mission proves suits, dust control, power, communications, tools, procedures, and human endurance. A repeat mission proves the system can recover, learn, rebuild, and fly again. The public memory tends to compress all of that into one word: moon. That compression is emotionally understandable. The moon is one object in the sky, so the mission feels like one object in the mind. But engineering never experiences it that way. Engineering experiences the moon as phases, interfaces, environments, and margins. The spacecraft is not trying to satisfy a sentence, it is trying to survive a sequence. One more way to see the problem is to imagine the mission as a door with many locks. Apollo opened a door once with a particular keyring. Artemis is not standing in front of that same door with the same keys. Some locks are familiar, some are new. Some are in different places because the destination and the standards changed. A crude flyby opens one lock, a landing opens another. A surface EVA opens another. Repeatability is what happens when the locks can be opened again without rebuilding the entire keyring each time. Now bring the point back to the title. The opening contradiction works because both halves are true. We already went, and going back is still hard. If either half is denied, the story becomes weaker. Deny Apollo, and we drift into conspiracy. Deny the modern difficulty, and we flatten the engineering. The stronger answer holds the tension. Apollo gives the question its bite. Artemis gives it its current evidence. The gap between reachability and repeatability gives the documentary its spine. From here, every constraint is one way of looking at that gap, until the simple sentence, "we already went," becomes true but no longer misleading. Apollo deserves precision before it deserves comparison. If we make Apollo small, the modern problem becomes too easy. If we make Apollo magical, the modern problem becomes impossible to explain. The correct starting point is simpler. Apollo was real, immense, and narrower than memory makes it feel. Between 1969 and 1972, 6 Apollo missions landed astronauts on the moon. 12 people walked there. They took photographs, deployed instruments, collected samples, drove across the surface on later missions, lifted off, rendezvoused in lunar orbit, and returned to Earth. Every part of that sentence should still sound astonishing. But Apollo was built around a specific question. Could the United States land a man on the Moon and return him safely to Earth before the decade was out? That goal shaped the machines, it shaped the urgency, it shaped the risk posture, it shaped the way the industrial system was assembled around one narrow national objective. Now look at the architecture. Saturn V launched the stack. The command and service module carried the crew through deep space and waited in lunar orbit. The lunar module separated, descended, landed, lifted off, and met the command module again. Then the crew came home. It was elegant because it was brutally focused. Every major piece existed to solve the mission as Apollo defined it. Apollo proved that humans could cross the distance. It proved that lunar orbit rendezvous could work. It proved that a small lander could descend and ascend in 1/6 gravity. It proved that humans could spend hours and eventually days on the lunar surface. It proved that a heat shield could bring a crew back from lunar return. These are not minor achievements. They are the foundation of everything that comes after. But the word proved has boundaries. Apollo proved those things with Apollo hardware, Apollo procedures, Apollo crews, Apollo landing sites, Apollo mission lengths, and Apollo-era acceptance of risk. It did not prove every future architecture. It did not prove polar operations. It did not prove a long-duration surface campaign. It did not prove that a different lander, different suit, different capsule, and different operational model would automatically inherit the same confidence. And that matters because engineering proof is not transferable in the casual way memory wants it to be. A bridge design that works in one river valley does not certify every bridge across every river. A spacecraft that works in one architecture does not certify another architecture just because both are called moon missions. Apollo also worked in a short window. The program did not mature into a standing route. It did not fly every few months for decades. It did not evolve into a permanent lunar transportation service. It did not leave behind fuel depots, habitats, power stations, South Pole landing pads, rescue architecture, or a continuing industrial rhythm that made lunar access ordinary. So when someone says, "We already did this," the honest answer is yes, and what we did was extraordinary. But the next question is more exact. Did Apollo prove that humans could reach the moon once, through a concentrated sprint? Yes. Did it prove that going to the moon had become routine, sustainable, and easy to restart half a century later? No. That is not an insult to Apollo. It is the reason Apollo still matters. Its success tells us the moon is reachable. Its limits tell us why reachability is not enough. Apollo also proved that people could make decisions far from Earth under pressure. The astronauts were not passengers in a simple machine. They were operators, pilots, observers, troubleshooters, and scientists inside a mission plan that depended on human judgment. That matters because lunar return is not only hardware. It is hardware plus procedure plus crew action plus ground support. The communication delay between Earth and Moon is roughly 1.3 seconds each way. That sounds small. Over a mission that lasts days, with decisions that sometimes cannot wait for a ground response, it means crews have to carry more of the decision authority themselves. Apollo crews were trained for this. The ground teams were built around it. The procedures anticipated it. A modern program has to do the same, building crew autonomy, real-time decision capacity, and abort logic that does not require a round-trip conversation with Earth at every critical moment. But again, the proof was bounded. Apollo crews trained for Apollo procedures in Apollo spacecraft. Their competence does not remove the need to train future crews for different vehicles, different displays, different failure modes, different suit interfaces, and a different surface environment. Human skill transfers broadly, certification does not. Apollo's narrowness is not a flaw. It is why the program succeeded. The goal had a sharp edge. Land a human on the moon and return that human safely to Earth. A sharp goal can organize a nation, a budget, an industrial base, and a technical culture. It gives thousands of decisions a direction. It tells engineers what must be optimized and what can be left for another era. That focus produced machines of extraordinary purpose. Saturn V existed to lift the mission stack. The command module existed to carry the crew through the journey and back through the atmosphere. The service module carried propulsion, power, and support. The lunar module existed for one world only. It never had to fly through air. It never had to look aerodynamic. It had to work in vacuum and low gravity. Descend, stand, and ascend. The lunar module is a perfect example of Apollo's genius and its limits. It solved Apollo's landing problem beautifully. But it was not a general-purpose lunar truck. It was not a reusable ferry. It was not built to support extended polar operations, large crews, or repeated surface logistics. It was a mission-specific answer to a mission-specific question. The same is true of the whole campaign. Apollo answered whether a trained crew, supported by a huge Earth-based system, could execute a carefully planned lunar landing and return. It did not answer whether humans could sustain a continuing presence. It did not answer how to operate through long polar darkness or near permanently shadowed regions. It did not answer how to make lunar access ordinary enough for a program that lasts decades. And that is where reverence and clarity have to live together. If we only revere Apollo, we may miss what remains hard. If we only emphasize what Apollo did not do, we may lose sight of how much it did. The right view is both. Apollo was one of the strongest demonstrations of human engineering ever flown, and it was not the same as a permanent transportation system. This matters for the viewer because it changes the emotional answer. Going back is not hard because the original achievement was fake or exaggerated. Going back is hard because the original achievement was real but bounded. The boundary is the lesson. Apollo also proved something about concentration. When a society focuses enormous resources on one technical objective, it can compress development time in ways that later seem almost impossible. But compression has a cost. The system is optimized for the deadline and the mission, not for permanent maintainability. It can produce a stunning result without producing a stable long-term institution around that result. This is easy to miss because the hardware looks so complete. A Saturn V does not look temporary. A lunar module does not look like a narrow answer. The command module in a museum looks solid, finished, almost inevitable. But the program around it was not inevitable. It was held together by urgency. When the urgency faded, the system did not continue on its own, and that is why Apollo can be both the proof and the warning. It proves humans can solve a lunar mission when the objective is clear and the resources align. It warns us that a solved mission is not the same as a permanent capability. A candle can burn brilliantly and still go out. Apollo burned brilliantly. The question now is not whether the flame was real. It is how to build something that stays lit. Apollo's proof belongs on the highest shelf. It demonstrated that humans could cross the distance, land, work, and return, through a specific architecture built around a specific mission, accepted on its own terms. That is not a small thing to have proven. But the boundaries of the proof are part of the proof. Apollo showed the moon was reachable. It did not show that reaching it had become ordinary. Everything after this point follows from that distinction. A successful expedition can change history without leaving behind an operating system. That is the uncomfortable middle of the moon story. Apollo did not fail after 1972. It ended, and when a system like that ends, something physical happens. The machines stop being built. The suppliers move on. The tooling is retired. The people scatter. The habits fade. But we need to be careful here. The lazy version says we lost the technology. That phrase is attractive because it sounds like a mystery. It suggests a locked drawer, a missing blueprint, a civilization that forgot its own trick. The real answer is less dramatic and more serious. We did not forget the moon. We stopped operating the machine that got us there. Now imagine trying to restart any old system exactly as it was, not just a rocket design on paper, the entire living ecosystem around it. The factories, the inspection methods, the specialized materials, the subcontractors, the human judgment inside teams that had built the same parts again and again. The test stands, the software practices, the documentation, the risk assumptions, the political urgency, the budget concentration, the suppliers that no longer exist in the same form. That ecosystem is not a museum artifact you can dust off and relaunch. It was a living network. Once it stops, it decays. Not because people become less intelligent, because technical capability is not stored only in drawings. It is stored in production, repetition, tacit knowledge, and teams that keep doing the work. Apollo also did not leave the moon prepared for our return. No runway waited there, no power grid, no communications network on the surface, no safe road from orbit to a landing zone, no dust-controlled airlocks, no permanent shelters, no rescue system, no supply cache. The lunar surface remained what it had always been, a vacuum world with abrasive dust, huge temperature swings, hard radiation, and no forgiveness for small mistakes, so the phrase going back can mislead us. It sounds like returning to a house we once lived in. But the moon is not a house. It is a place where every visit has to carry almost everything it needs, prove almost every step again, and bring the crew home through the same unforgiving physics. Apollo did not build a lunar logistics culture. It did not teach us how to operate at the South Pole. It did not certify modern life support systems. It did not solve modern spacesuit sizing and mobility. It did not test how a new commercial lander docks with Orion in lunar orbit. It did not show how to sustain repeated missions with international partners and multiple contractors across years. And this is where the old capability becomes emotionally confusing. The photographs are still fresh. The footprints are still there. The moon looks close because it is visible every night. But an achievement preserved in memory is not the same as an active capability preserved in industry. Think about aviation for a moment. If an airline stopped flying every wide-body aircraft for 50 years, closed the factories, retired the crews, dismantled the maintenance system, changed the regulations, and then decided to operate again, the fact that people once crossed oceans by air would not make the restart simple. The physics would be known, the history would be real, the operation would still have to be rebuilt. That is the Apollo gap, not forgetting, not fraud, not weakness, discontinuity. And discontinuity is expensive because it turns a former achievement back into a live engineering program. There is also a psychological problem in the long gap. Once enough time passes, the visible artifact becomes more powerful than the invisible system. We still see the Saturn V in museums. We still see the lunar module in photographs. We do not see the procurement offices, inspection rooms, machine shops, test stands, suppliers, handwritten expertise, and routines that made those objects fly. That invisibility makes restart look easier than it is. We imagine the vehicle as the capability, but the vehicle was only the visible tip of a capability. The rest was organization, practice, material flow, standards, software, test discipline, and urgency. Remove that hidden base, and the old shape no longer equals a living system. There is another layer of discontinuity. Requirements changed. A design frozen in the 1960s does not return unchanged into a modern certification environment. Materials rules change. Software expectations change. Documentation expectations change. Risk communication changes. Crew demographics change. Public oversight changes. The mission objectives change. Even if every Apollo drawing were available, a modern program would still have to ask whether the old part should be built the old way, whether the old supplier exists, whether the old material is acceptable, whether the old test captures the modern risk, and whether the old design serves the new destination. A blueprint is not a permission slip from physics. Now think about people. Institutional knowledge is perishable. Some of it is explicit, written down in specifications and reports. Some of it is tacit, carried in the hands and eyes of people who have built and tested the same kind of hardware many times. They know which measurement is suspicious. They know which noise is normal. They know which tolerance looks fine on paper but causes trouble in assembly. When a production culture ends, that living judgment thins out. That does not mean the knowledge is gone forever. It means reacquiring it takes work. New teams can learn. New tools can improve on old ones. Modern computing, materials, simulation and manufacturing can help. But learning still has to happen. The moon does not accept nostalgia as verification. There is also no permanent cadence to inherit. Repetition is what makes operations less mysterious. If lunar missions had continued every year after Apollo, the system would have evolved with practice. Instead, the gap became part of the problem. The less often humans do something, the more each return has to rebuild the habit around it. There is a phrase from manufacturing culture worth borrowing here. You cannot inspect quality into a product. Quality has to be built in through the process, the training, and the repetition. The same logic applies to spaceflight operations. A checklist does not automatically produce competence. Competence is what happens after teams have used the checklist enough times to understand where it is fragile, where it requires judgment rather than compliance, and where an experienced hand catches what a first reading misses. That kind of operational quality is not stored in documents. It develops in people over time and through work. Apollo's teams had it. The gap between programs meant it had to be rebuilt from a lower starting point. So the old question, why not just rebuild Apollo, starts to answer itself. Because Apollo was not only an object, it was a time, an ecosystem, a risk posture, a mission definition, and a national sprint. You can learn from it, you can honor it, you cannot simply press replay. There is a useful phrase from manufacturing: production is knowledge. Not all knowledge sits in the design file. Some knowledge is created only by making the thing repeatedly. Workers learn which steps are fragile. Inspectors learn which defects matter. Engineers learn which tolerances are theoretical and which are painful. Managers learn which suppliers are reliable. The whole organization becomes smarter through repetition. Apollo's production knowledge was real, but when production ends, knowledge stops being refreshed. Documents remain, but the living feedback loop is broken. Decades later, a new program can read the documents, but it cannot inherit all the repetitions that made those documents alive. It has to create its own production knowledge. This is why the restart problem is deeper than nostalgia. We can admire the old machine and still understand why rebuilding it is not the strongest path. The world changed around it, the mission changed beyond it, and the hidden knowledge inside its production rhythm was not preserved as an operating cadence. Going back means building a new living system, not worshipping an old one. That is the Apollo gap. Not failure, not forgetting, discontinuity, and what discontinuity teaches is that capability is not stored in achievements, it is stored in practice. The blueprint that sat untouched for 50 years is still accurate. The living knowledge that made it fly did not wait. A program does not end and resume unchanged. It ends, and the work of building it again belongs to whoever comes next. Now we can see why Artemis is not just Apollo with new paint. The point of Artemis is not merely to recreate a photograph. NASA describes it as a campaign, returning humans to the moon, reaching the lunar South Pole, building toward longer presence, working with commercial and international partners, and preparing for future Mars missions. Whatever one thinks of the exact architecture, that is a different problem from Apollo's sprint. The first difference is safety, not because Apollo ignored safety. Apollo was filled with brilliant safety work, but the program accepted a level of urgency, uncertainty, and concentrated risk that belongs to its historical moment. Modern crewed spaceflight has to justify itself through deeper verification, clearer failure analysis, more public review, and more inspectable decision-making. And when human beings are inside the spacecraft, a test is never just a test. Life support has to work. Carbon dioxide has to be removed. Temperature has to be controlled. Pressure has to be held. Waste has to be managed. Displays, software, sensors, propulsion, power, communications, abort modes, and recovery systems all have to behave well enough for the crew to survive, not just the planned mission, but credible off-nominal paths. That phrase, off-nominal, sounds dry. It means the moment when the mission stops following the poster, a valve sticks, a sensor lies, a communication path drops, a cabin system runs warmer than expected, a line freezes, a parachute deploys with a timing issue, a spacecraft returns a little differently than predicted. Serious human spaceflight is the art of asking what happens then. Apollo answered many of those questions for Apollo. Artemis has to answer them for Artemis. That is the central discipline. You cannot certify a modern vehicle by admiration for an old one. You certify it by test data, analysis, inspection, procedures, simulation, and flight experience in the environment it will actually face. Now add repeatability. A one-time sprint can lean harder on heroics. A repeatable system cannot. Repeatability demands margins. It demands standard work. It demands production quality that survives not once, but across vehicles. It demands that teams understand why something worked, not merely that it worked. It demands that anomalies become knowledge before they become habits. This is why a successful mission can still produce work. Artemis II can return safely, and NASA can still have follow-up items. That is not contradiction. That is how test programs mature. A crewed flight can prove a layer while also revealing small issues that must be understood before the next layer carries more risk. The modern moon problem is also distributed. Apollo had contractors and interfaces, of course. But Artemis spreads major functions across new spacecraft, new providers, new integration paths, and future surface systems. Orion is not the lander. The lander is not the suit. The suit is not the surface power system. The surface power system is not the communications path. Yet the mission depends on all of them behaving like one chain. Here is the quiet shift. Apollo had to show that humans could do the impossible once. Artemis has to show that the possible can become dependable. The first is dramatic. The second is less romantic and often harder, because it requires making extraordinary events repeatable enough to trust. So when we ask why going back is hard, we should not look for one villain. The hard part is the standard itself. Safer, repeatable, inspectable, sustainable. Those words sound bureaucratic until you place a crew inside a capsule and send it toward the moon. Then they become the difference between bravery and recklessness. Modern safety also changes how anomalies are treated. An anomaly is not merely a thing that did not destroy the mission. It is a thing that must be explained before confidence can grow. If a system survives but behaves unexpectedly, the survival is good news. The unexpected behavior is still information demanding attention. That distinction is crucial for long-form science because it keeps us away from hype. A test finding is not automatically a scandal. It is not automatically harmless either. It is evidence. The mature response is to ask what caused it, whether the cause is bounded, what mitigation exists, and what future flight conditions might change. Modern verification also has to deal with complexity that is harder to hide inside a single heroic narrative. If a spacecraft contains software-controlled systems, international hardware, commercial interfaces, new suits, and future surface goals, then proof becomes distributed. One team may own a vehicle, another may own a suit, another may own a lander, another may own ground systems. The crew experiences all of it as one mission. That creates a special kind of responsibility. Each component can be excellent in isolation and still create risk at the boundary. A display can be clear until a suited astronaut uses it. A hatch can be adequate until a pressurized body moves through it. A docking mechanism can be strong until contact dynamics expose a load path. A procedure can work in simulation until fatigue, lighting, timing, and communication delays change the human reality. So repeatability is not just about flying the same path twice. It is about building a system that can absorb variation. A slightly different vehicle, slightly different crew, slightly different surface lighting, slightly different landing conditions, slightly different post-flight inspection result. A mature system has margins and processes for that variation. An immature system may still depend on every assumption lining up perfectly. The moon is especially unforgiving because many rescue options are limited by distance and timing. If something fails on Earth, you may bring in more people, more tools, more power, more time. If something fails on the moon, the mission has what it brought, what it can improvise, and what orbital mechanics allow. That changes the standard before launch. Now put a crew inside that reality. We are no longer talking about an elegant machine on a diagram. We are talking about people who breathe from the system, drink from the system, hear alarms from the system, and depend on the system to interpret what is happening around them. Modern safety has to respect that human layer. A vehicle may have redundant hardware, but the crew also needs time, clarity, and procedures that make sense when pressure rises. That is why verification is not just a paperwork ritual. It is a way of buying calm before the crisis. Teams rehearse the awkward cases so that the real crew does not have to invent the answer from scratch. They ask which warnings matter first. They ask which valve can be closed manually. They ask what information the crew can trust if two sensors disagree. None of that looks heroic from the outside, but it is what lets heroism become unnecessary. And this is where modern caution should not be mistaken for timidity. Careful testing is not the opposite of exploration. It is the way exploration survives after the first heroic era. A program that wants to repeat has to be less romantic about uncertainty than a program racing a deadline. The strongest lunar system would eventually feel almost dull from the outside. Vehicles processed, crews trained, interfaces verified, anomalies understood, flights repeated. That dullness would be a triumph. It would mean the extraordinary had become operational. Human rating a system is also different from making it work once. A machine can perform and still not be acceptable for crew until its failure modes are understood. What happens if a valve fails closed? What happens if a sensor drifts? What happens if a computer resets? What happens if the crew has to take manual action at the worst possible time? These questions multiply because humans are not replaceable test payloads. The more ambitious the mission, the more those questions connect. A life support issue can affect crew workload. Crew workload can affect docking. Docking delays can affect consumables. Consumables can affect surface timelines. Surface timelines can affect ascent windows. The system is not a set of isolated boxes. It is a web of consequences moving through time. That is why modern lunar return can seem slower than the public expects. The visible act is simple: launch, fly, land. The invisible work is to make sure the mission still has an answer when the simple path bends. Safer repeatability is not a slogan. It is the discipline of preparing for the bend before people are inside the machine. So when the question is why going back is hard, this is one of the quieter answers. The hardest part is not the heroic act. It is the discipline of making a heroic act into a dependable one. Apollo accepted urgency as a condition. Artemis has to accept scrutiny as a standard. That is not timidity. It is the difference between a mission that succeeded once and a system that can be trusted to succeed again. Artemis II gives this story its modern anchor. It is tempting to turn that mission into the whole video because a crude lunar flyby is visible, recent, and easy to narrate as news. But that would shrink the question. The deeper value of Artemis II is not that it gives us a recap, it gives us a boundary. NASA says Orion carried Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen around the moon and back. The spacecraft splashed down safely off San Diego on April 10, 2026, after a journey of 694,481 miles. NASA's initial assessment says the entry interface velocity was within 1 mile per hour of prediction. The splashdown was 2.9 miles from the target site, and a thermal protection system performed as expected, with no unusual conditions identified. That is real progress. We should let it be real progress. A crewed spacecraft went into deep space, carried people around the moon, came back at lunar return speed, deployed its descent systems, and was recovered. For the transport layer, that matters. It moves Artemis from uncrewed demonstration toward crewed deep space operation. But now comes the important turn. Artemis II was not a landing mission. It did not ask the crew to transfer into a lander in lunar orbit. It did not descend to the South Pole. It did not test suited work on the surface. It did not send dust into suit joints and seals. It did not ask a lander to ascend and meet Orion again. It did not prove a repeatable surface campaign, so a good Artemis II result does not erase the title question. It sharpens it. We can now say, more clearly than before, that one major layer has been tested with crew aboard. And still, the larger lunar return system remains a chain of unproven or still maturing links. This is how engineering progress often looks from the outside, strangely unsatisfying. The public wants a single moment where the problem becomes solved. Engineers usually get a sequence of narrower truths. This worked. Under these conditions, with this configuration, with these observations, with these follow-up inspections still to come. The heat shield story shows that discipline. NASA's initial Artemis II inspections were encouraging. They found the thermal protection system performed as expected, and that the Artemis Shah loss behavior was significantly reduced in quantity and size. But NASA also noted that deeper review remained underway. Imagery review, desurfacing inspections, data retrieval, later sample extraction, and internal X-ray scans. That caveat is not weakness, it is the work of turning a flight result into trusted knowledge. NASA also reported a separate urine vent line issue requiring root cause work and corrective action before Artemis III. Again, this should not be inflated into drama, it is better understood as the ordinary seriousness of crewed test flight. A successful mission still returns with homework. The machine comes home, and then the evidence begins speaking in finer detail. Now hold Artemis II next to Apollo. Apollo proved landing and return in its own architecture. Artemis II proved a modern crewed flyby and return layer. Those statements are both strong, they are also different. We get into trouble only when we pretend one proof automatically covers the other. And this is why Artemis II belongs in the opening, but not as the spine. The mission tells us the path back is active again. The rest of the documentary explains why active does not yet mean routine. There is a reason NASA flew Artemis II before attempting a landing. Crewed systems need a crewed environment. The spacecraft can be tested uncrewed, and Artemis IV did that. But people change the mission. They use life support. They interact with displays. They sleep, eat, move, communicate, observe, and respond. A spacecraft with humans aboard is not the same operational system as a spacecraft without them. That is why the transport layer proof matters even though it is not the full proof. It gives the program real data about crewed deep space operations. It also gives future missions a firmer foundation. But a foundation is not the building. The landing chain still has to be constructed on top of it, and this is the point where the story changes shape. Up to Artemis II, the main question is whether a modern crew can travel through deep space, loop around the moon, and come home through the atmosphere safely. After Artemis II, the question becomes more physical, more local, and less forgiving. Can that crew leave Orion? Can another spacecraft meet them in lunar orbit? Can they transfer between vehicles without turning a routine handoff into the mission's most fragile moment? Can a lander leave orbit, descend toward uneven ground, throttle and steer precisely, stand on the surface, keep its systems alive, and then lift off again when the clock says it must? Those are not details added after the real mission. For a landing, they are the mission. The difference matters because transport proof and landing proof fail in different ways. A flyby asks a capsule to be a deep space lifeboat and a return vehicle. A landing chain asks multiple vehicles, interfaces, crew procedures, suits, power plans, surface timelines, and abort options to behave as one temporary organism. Each handoff creates a new place where confidence has to be earned. Docking has loads and alignment. Transfer has pressure seals and crew procedures. Descent has navigation and landing sensors. Surface work has dust and time pressure. Ascent has ignition, guidance, and rendezvous. None of those steps becomes proven just because the capsule did its job beautifully. This is where the simple public phrase going back becomes too small. A crewed flyby is going back in one legitimate sense. A crewed landing is going back in another. A repeatable surface campaign is going back in a third. Artemis II moved the first sense from plan into evidence. The second and third still have to earn their own evidence in the environment they actually face. So the landing chain is not an optional sequel to the Artemis II story. It is the next proof the title is asking for. If Artemis II tells us the road out and back is reopening, the landing chain asks whether the road has exits, bridges, work sites, and a way home after the surface has had its say. That is a harder claim, and it deserves its own proof. One useful way to understand Artemis II is to ask what would have remained unknown without it. Orion had flown uncrewed on Artemis I, but an uncrewed mission cannot fully test crew operations. It cannot show how a human crew lives inside the vehicle over the mission, how procedures feel in real time, how displays and timelines work with people aboard, how the cabin environment performs under normal human use, or how recovery unfolds with a crew waiting inside. So Artemis II added the human layer to deep space transport. That is a meaningful threshold. It is the difference between proving that a spacecraft can fly the path and proving that a spacecraft can carry people along that path. Life support, habitability, communications, crew workload, emergency logic, and recovery all become less abstract. But the mission was deliberately not asked to do everything. It did not carry the risk of a first Artemis landing on top of the first crewed deep space Artemis flight. That sequencing is part of the safety logic. Prove transport before landing. Prove return before surface operations. Reduce the unknowns before stacking more of them together. The public often experiences that as delay or caution. Engineers experience it as risk retirement. A risk retired in one mission is a risk the next mission does not have to carry in the same form. But the next mission still carries its own risks. Artemis III cannot borrow Artemis II's success as proof that a lander will descend correctly or that suits will perform at the South Pole. This is why the word layer matters. A layer can be successful and still not cover the whole structure. The foundation can be strong while the upper floors remain under construction. Artemis II strengthens the foundation. It does not magically complete the building, and that makes the story more optimistic, not less. We can acknowledge real progress without pretending progress equals completion. The moon does not become easier because a press release says so. It becomes less unknown because each tested layer returns evidence. Artemis II also helps correct a second misconception, that any unsolved later problem somehow cancels earlier progress. It does not. If HLS still needs testing, that does not mean Orion failed. If suits still need verification, that does not mean the crewed flyby was meaningless. A complex program advances unevenly because different parts mature at different speeds. The mature way to read Artemis II is therefore layered. It proves that crewed Orion deep space transport has passed a major flight test. It supports confidence in launch, mission operations, crew systems, re-entry, recovery, and post-flight assessment. It also leaves the landing architecture exactly where a flyby would leave it, needing its own proof. This protects the video from two bad stories. One bad story says Artemis II solved the moon. The other says anything short of a landing is irrelevant. Both flatten reality. The stronger story says Artemis II is a real step in a chain, and the chain is not complete until the landing and surface links have their own evidence. So Artemis II gives us a clean answer to one part of the question, and a cleaner boundary around the rest. The crewed transport layer has real modern flight evidence. The landing layer does not get to hide inside that success. It has to stand in the light on its own. That is not a pessimistic conclusion, it is a more useful one. Progress becomes strongest when we know exactly what it proves. Artemis II proved that the path around the moon and home can carry crew in this architecture. The next challenge is proving that the path can branch down to the surface, survive the surface, and close again. Until that happens, the hard part has not vanished. It has simply moved to the next link. Every moon mission has two destinations. One is the moon, the other is Earth's atmosphere on the way home. We talk about the first one because it is beautiful. We should talk about the second because it is unforgiving. Coming home from the moon is not like lowering an aircraft toward a runway. A returning capsule reaches Earth carrying enormous kinetic energy. NASA's Artemis II material describes entry at nearly 35 times the speed of sound. At those speeds, the atmosphere is not just air. It becomes a wall the spacecraft must enter carefully, at the right angle, with the right attitude, with a shield designed to be damaged in precisely the right way. The heat shield is not armor in the simple sense. It is a sacrificial system. Orion's heat shield uses Avacoat, an ablative material. Ablation means the shield protects the crew by being consumed. It chars, it erodes, it carries heat away as material leaves the surface. The spacecraft survives because part of it is designed not to survive unchanged. That idea is worth sitting with. The shield works by losing itself. Too little loss can mean heat is not being managed correctly. Too much loss, or loss in the wrong pattern, can threaten margin. The goal is not a perfect-looking shield after flight. The goal is a shield whose behavior is understood deeply enough that engineers can trust the protection it provides. Artemis I made this point sharply. The uncrewed Orion went around the moon and came home successfully, but post-flight inspection found unexpected heat shield char loss. NASA later identified a cause involving gases generated inside the avcoat during the skip entry environment. Those gases did not vent and dissipate as expected. Pressure built up, cracks formed, charred material shed locally. Now we need careful language. NASA said the Artemis II data showed a crew would have remained safe. The spacecraft did return successfully. This was not proof that lunar return was impossible. It was proof that the real flight environment can reveal material behavior that ground tests and models may not fully capture before the first mission. That is exactly why test flights exist. Spacecraft do not fly through textbook conditions. They fly through coupled reality. Speed, heating, pressure, angle, material response, manufacturing detail, atmospheric density, vehicle motion, and time. A heat shield is not simply a part bolted to the bottom of a capsule. It is a conversation between chemistry, airflow, thermal energy, structure, and uncertainty. Orion also uses skip entry. The simple picture is this. Instead of diving once all the way through the atmosphere, the spacecraft dips into the upper atmosphere, uses aerodynamic lift to adjust its path and range, skips outward, and then comes in again for final descent. This helps manage where the capsule lands and how energy is handled, but it also creates a particular heating and pressure environment that the shield has to tolerate. So when NASA explains the Artemis II char loss in relation to the skip entry environment, the point is not jargon. The point is that coming home is a dynamic maneuver. The capsule is not a stone falling into air. It is flying a narrow corridor through plasma, heat, pressure, and velocity. Artemis II then becomes the next evidence point. NASA's initial post-flight assessment was positive. The thermal protection system performed as expected, with no unusual conditions identified, and the Artemis II char loss behavior was significantly reduced. That is encouraging. It means the mitigations, understanding, and flight conditions produced a much better initial result. But the discipline remains. Initial assessment is not the same as final analysis. Engineers still review imagery, retrieve data, inspect the vehicle during deservicing, extract samples, and look inside the heat shield. They are not doing that because the mission secretly failed. They are doing it because repeatable human spaceflight requires knowing why the mission succeeded. Here is the deeper lesson. The atmosphere is our protection when we live on Earth. It burns meteors, it holds air, it gives us weather. But for a spacecraft returning from the moon, that same atmosphere becomes the most violent part of the trip home. The mission must use it without being destroyed by it. And this is why re-entry deserves a full place in the answer. The moon is not hard only because it is far away. It is hard because you have to come back from far away, with people inside, through a narrow physical gate that does not care how famous Apollo was or how successful the launch looked on television. A lunar mission is not finished when the spacecraft leaves the moon. It is finished when the heat shield has done its controlled sacrifice, the parachutes have opened, the capsule is floating, and the crew can be reached by recovery teams. Until then, Earth is still another destination. The parachute phase can seem gentler because it happens after the fire, but it belongs to the same survival chain. Drogs, mains, deployment timing, loads, winds, capsule attitude, and ocean recovery all matter. A capsule that survives heating still needs to slow, stabilize, splash down, remain safe in the water, and be reached by recovery teams. That is why the final minutes of return are not an afterthought. They are the moment when deep space energy becomes human rescue. The mission has crossed hundreds of thousands of miles, But the crew is not truly home until the vehicle is stable, the systems are safe, and hands can reach the hatch. The entry corridor is narrow in a way that is hard to feel from the ground. Too shallow, and a spacecraft can skip out too much or fail to manage its energy properly. Too steep, and heating and loads can become harsher. The vehicle has to meet the atmosphere at the right angle, with the right orientation, under conditions that are never perfectly identical to the model. At lunar return speeds, tiny differences can matter. Atmospheric density changes with altitude and conditions. Vehicle attitude affects heating and lift. The surface of an ablative material is changing as it works. The spacecraft is not simply enduring heat, it is using shape, material response, trajectory, and time to turn deadly energy into survivable descent. This is why ground testing is powerful but incomplete. Engineers can use arc jets, material samples, thermal models, computational fluid dynamics, and previous flight data. They can recreate pieces of the environment, but the complete coupled event is flight. The actual spacecraft, at actual speed, in the actual atmosphere, after an actual mission, creates the evidence no lab can fully replace. Artemis I's heat shield finding therefore belongs in the story as a science lesson. It shows that even after decades of spaceflight, the particular combination of material, geometry, skip entry, heating history, and pressure behavior can surprise engineers. Surprise does not mean ignorance, it means reality had one more layer to show. Artemis II's initial result then becomes the next turn. The thermal protection system performed as expected, NASA said, and the Artemis II's Shale loss behavior was much reduced. That is exactly the kind of progress a test program wants. Identify, understand, mitigate, fly, inspect, learn again. The final answer on any heat shield is never just, did it look good from outside? It is, what did the temperatures do? What did the material do? Where did the SHA go? What did imagery show? What do samples reveal? And how much margin remains for future missions? That is the level of knowledge repeatability asks for. Re-entry also reveals why spaceflight is not only about distance. In one sense, the moon is far away. In another sense, the hardest minutes may happen when the spacecraft is almost home. The crew can be close enough for Earth to fill the window and still be separated from safety by speed, heat, plasma, parachutes, and ocean recovery. That is a powerful inversion. We imagine danger decreasing as the spacecraft approaches Earth. Physically, some dangers peak during return. The atmosphere is what allows the spacecraft to slow without carrying impossible amounts of fuel. But using the atmosphere means entering a violent energy exchange. The capsule survives because its shape, materials, trajectory, and guidance have been tuned to turn that violence into deceleration. Apollo proved lunar return re-entry could be survived. Orion has to prove how Orion survives it. Artemis I exposed a specific behavior. Artemis II delivered an encouraging initial result. Future analysis turns those flights into design confidence. This is the rhythm of returning from the moon. Fly, inspect, understand, improve, and never forget that Earth's atmosphere is both the last obstacle and the way home. Re-entry belongs in the answer to the title, not because it goes wrong most of the time, because it is where the entire outbound journey has to be paid for at once. The moon may be the destination the crew dreams of. Earth's atmosphere is the destination the crew has to survive, and that atmosphere does not respond to reputation. It responds to physics, angle, and the material behavior of a shield no one will see until it comes back changed. Before we leave re-entry, notice how much of this whole problem depends on humility. The spacecraft can look simple from the outside: blunt capsule, dark heat shield, parachutes, ocean. But underneath that simplicity is one of the most carefully managed energy problems humans attempt. The vehicle is moving too fast to land, carrying too much energy to ignore, and returning to the only planet in the story with an atmosphere thick enough to help and hurt at the same time. This is why re-entry is such a useful correction to the phrase going to the moon. The phrase points outward. It makes the journey sound like departure. But a lunar mission is equally a return problem. If the return system is not trusted, the mission is not trusted. The moon may be the destination we dream about, but Earth is the destination the crew must survive reaching, and repeatability raises the standard again. One safe return is a triumph. Many safe returns require a system that behaves predictably across manufacturing batches, flight profiles, inspection results, and mission conditions. The heat shield has to be more than heroic. It has to be understood. The parachutes have to be more than successful. They have to be reliable. Recovery has to be more than dramatic. It has to be procedural. So when Artemis II returns safely, the right reaction is not to close the book. It is to read the book more carefully. The flight gives engineers data that no meeting could provide. The initial result is encouraging. The deeper review is part of making that encouragement durable. This is how a test flight becomes a step toward routine access, rather than just a beautiful event. After Orion proves that it can carry crew around the moon and bring them home, the next problem is not simply doing the same thing lower. A landing mission changes the geometry. The mission becomes a chain in lunar orbit. For Artemis III, as NASA describes it, Orion carries the crew to lunar orbit. Then it must dock with a separate human landing system. 2 astronauts transfer from Orion into that lander. The lander descends to the lunar south pole, supports surface operations, lifts off again, returns to Orion, transfers the crew back, and then Orion brings them home. That sequence sounds clean when written as a sentence. In reality, every comma is an interface. 2 spacecraft have to find each other far from Earth. They have to approach at controlled speeds. They have to align. They have to touch gently enough not to damage structures, but firmly enough for capture mechanisms to engage. Loads have to move through the docking system. Seals have to hold. Hatches have to open. People in bulky suits or confined clothing have to move through the passage. Procedures have to work when the crew is tired, weightless, and far from help. This is why NASA and SpaceX testing of a full-scale Starship HLS docking adapter matters. Not because a docking ring is glamorous, because a docking ring is where architecture becomes contact physics. It is where a mission diagram becomes metal touching metal. Apollo also used lunar orbit rendezvous. That is important. Artemis did not invent the idea that separate vehicles can meet around the moon, but Apollo's success does not automatically certify Artemis hardware. The vehicles are different. The interfaces are different. The mission objectives are different. The lander is different. The verification path is different. Now think about dependency. If launch works but docking does not, there is no landing. If docking works but the lander is not ready, there is no landing. If the lander works but the suit interface fails, surface operations shrink or stop. If ascent works but rendezvous has a problem, the return chain is threatened. Lunar landing is not one heroic descent. It is a choreography of linked truths. GAO's public warnings about lander and spacesuit development are useful here not as blame, but as structure. Sequential tests create ripple effects. Some tests must happen before later tests. Some data must exist before a system can be accepted. A delay in one link is not an isolated calendar problem. It can hold the entire chain because the next step depends on evidence from the previous one. This is the kind of difficulty that rarely fits into a thumbnail. The viewer sees a rocket. The viewer sees a capsule. The viewer sees an astronaut on a ladder. But much of the real risk is hidden in transitions. Between spacecraft, between environments, between procedures, between systems owned by different teams, and that should change how we hear the phrase going back. Going back does not mean one spacecraft points at the moon and lands. It means a crew crosses a sequence of handoffs. Earth to launch vehicle to Orion, Orion to deep space, Orion to lunar orbit, Orion to lander, lander to surface, surface back to lander, lander back to Orion, Orion back to Earth, Earth's atmosphere back to ocean recovery. Every handoff is a place where the mission must be understood. Every handoff is a place where Apollo can inspire but not certify. Distance changes rescue logic. In low Earth orbit, help is still hard, but options can be closer. Around the moon, the system has to carry more of its own answers. Timing windows, consumables, orbital mechanics, and communication delays are not science fiction obstacles. They are operating conditions that shape what crews can safely attempt. So when we picture lunar orbit, we should not picture an empty stage where spacecraft simply meet. We should picture a narrow timetable. Fuel is being spent. Batteries and life support consumables are being counted. Ground teams are watching through delay and geometry. The crew is following procedures that were built years earlier from tests, simulations, and assumptions about how the vehicles would actually behave. If the first approach is waved off, the question is not only whether the vehicles are safe in that instant, the question is what the wave off does to the rest of the mission. How much propellant remains? How much time remains? Does the lander stay in the right orbit? Does Orion have the right position to try again? Can the crew rest, troubleshoot, and reconfigure without eating into a later safety margin? We can feel the difficulty here because it is not one dramatic failure point. It is the arithmetic of options narrowing. So lunar orbit docking is not only a mechanical event, it is a commitment point. Once astronauts transfer into the lander, the mission has crossed from transport into surface access. The chain has narrowed. The options have changed. That is why every interface before that point has to earn trust. Orbital rendezvous also forces humility, because it turns timing into survival. Spacecraft cannot simply stop and wait wherever they like. They move along paths governed by gravity, velocity, fuel, and mission design. To meet, they have to be in the right orbit at the right time, with enough propellant, navigation accuracy, communication, and system health to complete the approach. There is a particular tension in lunar rendezvous that low Earth orbit missions do not face in the same way. Around Earth, a chase vehicle can make multiple orbit corrections over hours, with ground teams watching closely and intervening quickly. Around the Moon, communication delays and orbital geometry compress the timeline. If a rendezvous approach goes wrong and has to be aborted, the lander does not simply wait. It is burning fuel in an orbit that is decaying in its own way, and the window to try again is not unlimited. The math of rescue is harder when both vehicles are 250,000 miles from the nearest repair option. This is why abort logic matters before the crew ever transfers. What happens if docking fails on the first attempt? What happens if a sensor gives a false reading during final approach? What happens if the lander has a propulsion anomaly at close range? Each of these scenarios has to have a planned answer, not because any of them are expected, because a mission that can only succeed when everything goes as planned is not ready for lunar orbit. A docking interface has to manage more than physical contact. It has to support alignment cues, relative motion, structural loads, capture, sealing, power or data pathways if needed, hatch operations, pressure checks, and abort options. Each of those words hides design work. Each can be tested partly on Earth. Each still has to be trusted in lunar operations. Now add crew psychology and workload. A transfer between spacecraft around the Moon would not feel like moving between rooms in a building. It would happen inside a mission timeline, with suits, checklists, communications, and awareness that the lander is a separate return critical system. The crew has to trust not only the vehicle they are leaving, but the vehicle they are entering. This is why interfaces are often where systems reveal their maturity. A mature system makes the handoff feel routine. An immature one turns the handoff into a major event. Artemis is still proving these handoffs. That does not make the architecture bad. It means the architecture is not yet boring. And boring is the target again. The day a lunar orbit docking feels procedurally ordinary will be the day a huge amount of hidden engineering has succeeded. Until then, it remains one of the places where going back to the Moon is still hard. There is also a philosophical difference between a vehicle and an architecture. A vehicle can be tested as an object. An architecture has to be tested as relationships between objects. Artemis landing depends on relationships. Orion to HLS, HLS to suit, suit to astronaut, astronaut to surface, surface systems to power, surface timeline to ascent, ascent to rendezvous, rendezvous back to Orion. Relationships are where hidden assumptions live. The lander may have enough volume, but can the crew move through it efficiently in suits? The docking system may capture, but can the full sequence be performed under realistic timing? The surface plan may fit on paper, but does it survive delays caused by dust, lighting, or fatigue? For fatigue, each relationship is a place where a clean diagram meets messy operation. Apollo had relationships too, and Apollo solved them for its own mission. Artemis has to solve a new set. That is why lunar orbit becomes more than a location. It becomes the hinge between going near the moon and going down to it. Everything before docking says we can arrive. Everything after docking asks whether we can operate. Lunar orbit is where the mission stops being a journey and becomes a sequence of commitments. Once a crew transfers into the lander, the options have narrowed. The margin for error belongs to whatever the engineering has already put in place. That is why every interface before the surface has to hold, not because failure is likely, but because at this distance, with these consumables, failure cannot be improvised away. Docking around the moon is the hinge. Everything before it brings the crew there. Everything after depends on what the hinge can hold. The lander is easy to misunderstand because the most famous image of lunar landing is a ladder. An astronaut climbs down. A boot touches dust. A sentence is spoken. History changes, but a lander is not a ladder. It is the bridge between orbit and a world with no runway, no air, no emergency services, and no second chance built into the landscape. For Artemis, that bridge has to descend, support humans, interface with suits, manage power and thermal conditions, provide a way out and back in, and then lift off again to meet Orion. A flyby can test a crew capsule. A landing tests a different class of problem. Engines have to throttle and guide descent. Navigation has to identify hazards. Structures have to survive landing loads. The vehicle has to stand safely on uneven terrain. The crew has to exit, work, and return. The ascent system has to ignite after exposure to the lunar surface environment. Then it has to find the waiting spacecraft again. Now add the actual Artemis architecture. The human landing system is not just a small Apollo-style module recreated from memory. NASA's current plan uses a separate lander with its own development and test path. Hardware evaluations include airlock layout, deck space, elevator use, handrails, clearances, controls, and how suited astronauts move through the system. Those details sound small until you imagine discovering on the moon that a suited astronaut cannot move the way the design assumes. A suit changes the body. It makes shoulders larger. It changes grip. It changes how far someone can bend. It changes vision. It changes fatigue. So a lander cannot be designed for an abstract person. It has to work for a pressurized human system that is already a spacecraft in miniature. This is why integrated testing matters. You can animate a lander descending forever. You can draw a clean airlock. You can show an astronaut floating from Orion into the lander. But eventually hardware has to answer questions drawings cannot answer. Can the crew reach the controls? Can they move through the hatch? Can they use the elevator? Can they handle tools? Can emergency procedures be performed in the volume available? Can the system be operated when something is awkward, delayed, or partially degraded? The lander also has to interact with the surface. Descent engines disturb dust. Landing legs meet uneven ground. Sensors interpret shadows and terrain. Thermal conditions change as sunlight and darkness move across the site. The vehicle has to keep itself and the crew alive without the protective envelope Orion provides during transit. This is where the moon stops being a destination in the sky and becomes a place. A place has surfaces, slopes, shadows, temperatures, dust, mechanical contact, human motion, maintenance problems. A place fights back in ways a flyby never experiences. We should avoid turning this into a tribal argument about one company or one rocket. The more useful point is architectural. When the landing function is separated from the crew transport function, the mission depends on the interface between them and on the readiness of both. That can be powerful. It can also be complex. Complexity is not failure. It is something that has to be proven. Now we can see why the lander deserves more than a footnote. If we only picture the ladder, we miss the machine that makes the ladder possible. If we only picture touchdown, we miss the return path. The lander has to be a bridge, shelter, elevator, launch platform, navigation system, power system, and emergency asset. We are asking one vehicle to turn lunar orbit into human work on the surface, then turn that surface work back into a rendezvous. That is a lot to ask of a single link, so the lander becomes one of the central answers to the title. Going back is hard because flying around the moon and landing on the moon are different verbs. One circles the destination, the other touches it, supports human bodies on it, and then escapes it again. Apollo did that once through its own machine. Artemis has to do it through a new one. Testing a lander is also hard because Earth is the wrong place in almost every way. Gravity is stronger, air exists, the lunar surface is not available for rehearsal. Engineers can test engines, structures, software, mock-ups, procedures, and analog environments, but the complete integrated descent and ascent in lunar gravity happens at the moon. That does not make the task impossible, it makes the evidence precious. Each ground test answers part of the question, each simulation narrows uncertainty, each hardware evaluation catches awkward realities, but the final environment remains the final examiner. Descent propulsion is one of the places where this is sharpest. A lunar lander cannot glide. There is no atmosphere to generate lift, no drag to slow a fall, no second chance if the engine misfires at low altitude. The descent engine has to throttle precisely, which means it has to modulate thrust across a wide range, while the vehicle is also adjusting attitude, reading terrain sensors, and managing fuel. Too much thrust and the vehicle rises, too little and the ground arrives faster than the plan assumed. The correct answer changes as the lander descends, because the mass changes as fuel burns and the terrain changes as the vehicle moves toward its selected point. Landing legs add another layer. They have to absorb the final contact loads without tipping the vehicle on slopes, without sinking into regolith that may be softer or harder than expected, and without compromising the ascent stage that sits on top of them. The ascent stage is not the same vehicle as the descent stage. It uses the descent stage as a launch platform. That platform has to be stable, level enough for the ascent engine to fire safely, and structurally sound after sitting in the thermal environment of the lunar surface for however long the crew is outside. The lander also carries the psychological weight of commitment. While the crew remains inside Orion on a flyby, the mission has not touched the surface problem. Once astronauts enter the lander and descend, the mission has chosen a narrower path. The lander must not only reach the surface, it must preserve the option to leave. That makes ascent as important as descent. The public imagination focuses on touchdown because that is where the drama is visible. But for the crew, the ascent engine and ascent sequence are the way home. A lander that reaches the surface but cannot leave has not completed the mission. It has become a trap. Surface support matters too. The lander may be a habitat for a limited period, an airlock, a power source, a communications node, a shelter, and the staging point for EVAs. It must function while sitting in dust, light, shadow, vacuum, and thermal extremes. It has to be designed not only for the ideal timeline, but for delays, crew fatigue, and contingency procedures. A larger lander can offer more volume or capability, but size does not remove difficulty. It can create new questions: how astronauts move between levels, how elevators or platforms behave, how dust is controlled, how emergency return is handled, how engines interact with the surface, how landing stability is assured, and how human factors hold up in bulky suits. So the lander is the moment where mission architecture becomes lived reality. It is where the moon stops being a destination on a trajectory plot and becomes a surface under landing legs. That transition is one of the hardest parts of the whole chain. Descent itself is a special kind of trust. There is no atmosphere for wings, no runway, no tower guiding a gentle approach in familiar air. The lander has to manage propulsion, navigation, hazard avoidance, and touchdown in a landscape where dust can rise, shadows can hide relief, and communication with Earth is not the same as being remote controlled from Earth. The crew may be aboard, but the vehicle has to do much of the precise physical work. It must know where it is, how fast it is moving, what terrain lies below, and whether it can still choose a safe place to settle. A landing system that is almost right can still be wrong in a way that matters, because touchdown is the moment the moon stops being a target and becomes a load-bearing surface. Then, after all that, the lander has to wait. It has to remain healthy while the crew works outside. It has to keep enough power, thermal control, communication and ascent capability. It has to be ready not only for the planned departure, but for the departure needed if surface operations are cut short. That waiting is part of landing too. The lander is therefore the problem Apollo's success left open. Apollo proved the moon could be landed on once through one machine at equatorial sites chosen for their accessibility. The next lander has to prove the same thing for a new architecture, a new set of standards, and a destination Apollo never aimed for. It cannot borrow its confidence. It has to earn its own, starting with descent and ending only when the ascent stage fires and finds the spacecraft waiting where it should be. The most familiar object in lunar exploration may be the most underestimated one. A spacesuit looks like clothing because a human wears it. That is the trap. A lunar spacesuit is not clothing. It is a spacecraft shaped around a body. It has to hold pressure. It has to provide oxygen. It has to remove carbon dioxide. It has to manage heat. It has to allow vision, communication, movement, tool use, sampling, climbing, kneeling, recovery from a stumble, and survival in vacuum. It has to do all of this while being scraped by dust, bent at joints, exposed to sunlight and shadow, and worn by different human bodies. Apollo suits worked for Apollo. That statement is not small. They allowed astronauts to walk, collect samples, deploy instruments, drive, and return. But Artemis suits have to answer a broader set of expectations. NASA and Axiom describe the AxiomU effort around improved mobility, wider sizing, life support, harsh environment protection, and extensive testing. NASA has cited hundreds of hours of pressurized testing with a person inside, along with underwater and simulated lunar gravity work. Now picture why that testing exists. An astronaut needs to bend to pick up a sample. The suit resists bending because it is pressurized. The glove has to protect the hand, but still allow enough dexterity to grip a tool. The helmet has to protect and provide visibility, but glare and shadow can make vision difficult. The boots have to work with dust and slopes. The life support backpack has to keep the astronaut alive while not making movement impossible. Every ordinary human action becomes engineered. Kneeling is engineered, standing up is engineered, turning around is engineered, reaching a control is engineered, walking through an airlock is engineered, brushing against a handrail is engineered, because abrasion, fabric wear, and dust contamination all matter. This is why suit development cannot be treated as costume design. A suit failure is not a clothing failure. It is a spacecraft failure wrapped around a human being. If pressure is lost, the body is exposed to vacuum. If cooling fails, heat becomes dangerous. If mobility is too limited, geology tasks become impossible, or emergency movement becomes slower. If dust enters seals and joints, repeated use becomes harder. The suit also connects to the lander. Hatches, elevators, handrails, controls, tool storage, airlock procedures, and dust control all depend on how the suited body actually moves. A lander design that works for an unsuited engineer in shirt sleeves may not work for a pressurized astronaut on the moon. Apollo taught us this in miniature. Astronauts adapted constantly. They hopped, leaned, fell, recovered, improvised, and learned how 1/6 gravity changed movement. Artemis inherits the lesson, but not as a solved problem. Modern suits have to serve a wider range of bodies and support more ambitious surface work at a harder destination. And here again, the title question becomes more concrete. Going back is not just sending humans to the moon, it is making human bodies temporarily compatible with the moon. The suit is the interface. Without it, the surface is not a workplace. It is vacuum, dust, radiation, and temperature waiting against skin. So when we see an astronaut in a lunar suit, we should not see a symbol first. We should see a small moving spacecraft. and every step it takes is one more link in the chain Artemis has to prove. There is another quiet challenge: sizing. Apollo crews represented a narrower range of bodies than a modern astronaut corps. A modern suit has to serve more people. That is not only fairness, it is operational capability. If the suit only works comfortably for a narrow body type, the mission design is constrained before the rocket ever launches. Mobility is also science. A geologist who cannot kneel, reach, turn, or see well cannot collect the same evidence. A suit that makes movement too exhausting shortens useful work time. So better suit design does not merely make astronauts comfortable, it changes what the mission can learn from the Moon. The life support system carried on an astronaut's back is where the suit becomes most obviously a spacecraft. The primary life support system has to supply oxygen, remove carbon dioxide, control temperature, manage humidity, circulate cooling water through a garment worn next to the skin, power the suit's electronics, and feed data to both the astronaut and the ground. It has to do all of this continuously for the duration of an EVA without a way to open a hatch and get help. Carbon dioxide removal is one of the less dramatic but more critical functions. A pressurized suit is a sealed volume. An astronaut breathing inside it generates CO2 steadily. If that CO2 is not removed, it accumulates. The consequences of CO2 buildup in a sealed environment are not subtle. So the scrubbing system has to work reliably, and the consumable it uses has to last the full EVA plus margin. The South Pole adds a thermal wrinkle. Temperature swings between sunlit and shadowed terrain are severe, and the suit's thermal management has to handle an astronaut who may move between both in the same excursion, generating different amounts of metabolic heat in different environments. A suit has to make pressure livable without making motion impossible. That is a deep design tension. A balloon wants to stay stiff when pressurized. A human body needs joints. Every shoulder, elbow, wrist, hip, knee, ankle, glove, bearing, seal, and fabric layer becomes a compromise between protection and movement. Thermal control adds another compromise. In sunlight, the astronaut can absorb heat. In shadow, the environment can be brutally cold. Inside the suit, the human body is generating heat through work. The suit has to reject heat, retain heat, and control humidity while remaining sealed against vacuum. There is no breeze, no open window, no easy way for sweat and heat to behave as they do on Earth. Vision is not simple either. A helmet protects the head and maintains pressure, but the astronaut has to see terrain, tools, handholds, samples, displays, shadows, glare, and other crew members. At the South Pole, with low sun and high contrast, vision becomes part of mission safety. A suit can be technically alive and still operationally frustrating if the person inside cannot see and move well. Communication is another lifeline. The suited astronaut has to speak with crewmates, the lander, and mission control through systems that work across posture, movement, terrain, and contingency. A surface EVA is a human activity mediated by electronics, pressure garments, procedures, and trust. This is why suit verification takes time. It is not enough for a suit to hold pressure in a lab. It has to support work. It has to support geology. It has to support emergency recovery. It has to support different bodies and different tasks without turning every movement into a fight against the garment. The suit is also where exploration becomes intimate. A rocket can be huge. A lander can be distant. A suit is pressed against the body. If it pinches, resists, fogs, overheats, limits reach, stiffens the hands, or makes balance awkward, the astronaut feels the engineering immediately. The Moon is experienced through the suit. That makes suit design one of the most human parts of the entire architecture. A better joint can mean a better sample. A clearer visor can mean safer walking. Better glove mobility can mean less fatigue. Better dust protection can mean longer hardware life. Better sizing can mean more astronauts are eligible to do the work. These are not cosmetic gains. They become mission gains. And because the suit is so close to the human body, it has to be trusted emotionally as well as technically. An astronaut stepping away from the lander is trusting a personal spacecraft with every breath. That trust is built through testing, verification, and experience. Apollo suits earned it for Apollo. Artemis suits must earn it for Artemis. And this is the smallest scale version of the whole title problem. Going back to the moon is hard because every layer of the chain has to hold, including the one pressed directly against a human body. The suit is not background equipment. It is the outermost wall between the crew and the surface. Apollo suits earned that trust for Apollo missions, in Apollo conditions. Artemis suits have to earn it for a harder environment, a wider range of bodies, and more ambitious work than any prior suit was designed to support. The moon's most memorable enemy may not be distance, or cold, or radiation. It may be dust. That sounds almost absurd. Dust is what we wipe from shelves. Dust is what gathers in corners. On Earth, dust is usually an annoyance. On the moon, dust becomes an engineering condition. Lunar dust is different because the moon is different. There is no rain to wash particles smooth, no wind to weather them in the earthly sense. No rivers, no soil cycle, no softening biological world. The surface is ground by impacts. Tiny particles can be sharp, abrasive, and clingy. They can stick electrostatically. They can ride suits back into a cabin. They can get into places where machines prefer cleanliness. Apollo astronauts learned this quickly. Dust coated suits. It entered the lunar module. It clung to surfaces. It irritated eyes and throats. It made equipment dirty in ways that mattered operationally. For short missions, crews could tolerate and manage it. But Artemis is not only trying to repeat a short visit, it is aiming toward longer, more capable, more repeatable surface operations. That changes dust from nuisance to design driver. Think about seals. A seal works because surfaces meet cleanly enough to hold pressure or block contamination. Now imagine abrasive powder working its way into that meeting place. Think about joints. A joint works because parts move against each other in a controlled way. Now add sharp particles. Think about optics. Cameras, sensors, visors, and navigation systems depend on seeing clearly. Now coat them with powder that wants to cling. Radiators and thermal surfaces care about dust too. A spacecraft or surface system has to manage heat. If dust changes how a surface absorbs or emits heat, thermal control becomes harder. Solar panels care. Bearings care. Fabrics care. Airlocks care. Lungs may care, which is why health risk has to be treated carefully and mitigated seriously, even when exact outcomes depend on exposure and controls. The deeper point is not that dust alone stops a moon mission. It does not. Apollo worked. The point is that dust touches many parts of the chain at once. It is a small thing that becomes large because it crosses boundaries. Suit to cabin, boot to floor, surface to mechanism, environment to human health, geology to engineering. And this makes lunar operations different from the clean imagery we often carry. The moon in photographs can look still, silent, almost polished. But the working moon is granular. It scratches, it clings, it follows astronauts indoors. It settles onto surfaces that need to reject heat or absorb sunlight. It tests the patience of seals and hinges. Now connect dust back to repeatability. A one-time mission can accept some mess. A repeated campaign has to manage accumulation. What happens after the first EVA, and the second, and the third? How do you clean suits? How do you keep dust out of living volume? How do you protect bearings, visors, connectors, radiators, sample containers, and docking or hatch surfaces? How do you inspect what dust is doing before it becomes a hidden failure mode? This is where the moon becomes less romantic and more real. The surface is not just where the astronaut stands. The surface is an active participant in the mission. It enters the hardware. It follows the crew. It changes maintenance. It turns every return to the airlock into a contamination event that has to be anticipated. So if someone asks why going back is still hard, dust may sound too small to mention. That is exactly why it matters. The hardest systems are often not defeated by one giant obstacle. They are worn down by tiny things repeated often, in the wrong place, under conditions where repair is difficult. Apollo saw the dust. Artemis has to live with it longer. Dust is also a time problem. On a single excursion, contamination may be manageable. Across repeated EVAs, it becomes cumulative. Every cycle through an airlock is a chance to import particles. Every movement can grind dust into fabric or mechanisms. Every cleaning procedure consumes time, power, attention, and a design margin. Part of what makes lunar dust unusual is its electrostatic behavior. On Earth, dust particles are rounded by water, wind, and biological processes. Lunar regolith has never experienced any of those. Its particles are angular, glassy, and sharp at a microscopic level. They also accumulate electrostatic charge from solar wind and ultraviolet radiation. That charge makes them clingy in a way that passive brushing cannot always overcome. Standard cleaning methods that work on Earth may not work well on the Moon because the physics of adhesion is different. Apollo astronaut Harrison Schmitt, the only trained geologist to walk on the Moon, reported a reaction after returning from an EVA that resembled hay fever. Sneezing, watery eyes, a sore throat. The cause was almost certainly lunar dust that had entered the cabin despite precautions. On a 3-day stay, crews could manage that. On longer missions with repeated EVAs, the same exposure would accumulate. Dust is therefore not only a mechanical and thermal problem, it is a human health variable that has to be treated as an engineering input, not an inconvenience to be tolerated. This is why dust mitigation is not housekeeping. It is mission architecture at a small scale. Brushes, coatings, suit ports, airlocks, seals, operational rules, and cleaning methods all become ways of defending the rest of the system from the surface it came to explore. Dust also changes the inside of the mission. A spacecraft cabin is a controlled environment. Pressure, oxygen, electronics, filters, switches, displays, fabrics, and connectors all prefer cleanliness. The lunar surface does not care. Every time an astronaut returns from outside, the boundary between the Moon and the cabin has to be defended. Apollo crews could smell dust. They could see it floating and settling. They could feel its presence. That sensory detail matters because it turns an abstract hazard into a human one. Dust is not just a line in a requirements document. It is something that follows the astronaut home and reminds the crew that the surface has entered the spacecraft. For longer operations, dust control becomes a habit. Where do dusty suits go? How are gloves cleaned? How are seals inspected? How are filters maintained? How do crews avoid breathing or spreading particles? How much time is spent cleaning instead of exploring? How much equipment lifetime is lost to abrasion? The answers may involve design choices like suit ports, better materials, coatings, electrostatic dust removal, dedicated cleaning procedures, and operational limits. But each answer has cost, mass, complexity, and failure modes. There is no free defense against the surface, and this is the pattern again. The Moon is not one obstacle. It is many ordinary-looking obstacles made severe by vacuum, distance, and repetition. Dust looks small until it becomes a maintenance system. Dust also creates a kind of humility because it refuses to stay in the category we assign it. We want dust to be geology when we study it, dirt when we clean it, contamination when it enters a seal, and health concern when it floats in a cabin. On the Moon, it can be all of those at once. That category-crossing quality is why it belongs in the center of the story. The same material that holds scientific clues about the Moon's history can damage the equipment used to study it. The surface is both archive and adversary. The astronaut wants to collect it, but the spacecraft wants to keep it out. A repeatable lunar program has to live with that contradiction. It cannot simply avoid dust because the entire Moon is covered in regolith. It cannot treat dust as harmless because Apollo already showed it was operationally serious. It has to build habits and hardware around a substance that is everywhere, clingy, abrasive, and patient. Dust is not the most dramatic problem on this list. That is exactly what makes it important. The dramatic problems announce themselves. Dust moves quietly into the places where it is not supposed to go, and stays. A program that cannot answer for the small continuous threat cannot be fully trusted with the large ones. The Moon's entire surface is the same patient, abrasive material. Learning to live with it, not just visit it, is part of what turning a landing into a repeatable operation actually requires. Apollo did not land everywhere on the Moon. That sounds obvious, but it changes the whole story. The Moon we remember from Apollo is not the full operating environment Artemis is aiming at now. The lunar South Pole is scientifically attractive precisely because it is different, and because it is different, it is harder. NASA focuses on the South Polar region because it may preserve volatiles, including water ice, in permanently shadowed areas. It also offers access to ancient terrain and science that can help reveal the Moon's history and the history of impacts across the inner solar system. So the destination is not random, it has a reason, but the same features that make the region valuable make it operationally strange. Near the lunar poles, the sun can sit low against the horizon. Light skims across the terrain. Shadows become long, sharp, and persistent. A crater rim may catch sunlight, while a nearby depression remains in deep cold. Terrain can look flat until shadow reveals relief, or hide hazards because contrast overwhelms the eye and senses. NASA visualizations of South Pole illumination show a world of sliding light and black geometry. The sun does not behave the way our Apollo mental picture expects. It moves low, it throws shadows sideways. Darkness is not just night. Sometimes, darkness is terrain blocking the low sun. Permanently shadowed regions can remain extremely cold because sunlight never reaches them directly. Now imagine landing there. A landing system has to identify safe ground in high contrast. It has to interpret slopes, rocks, shadowed depressions, and lighting that can deceive perception. Astronauts have to walk or work where glare and darkness can sit close together. Rovers or tools have to navigate without the easy visual cues we take for granted. Power becomes a planning problem. Sunlight is valuable because solar power depends on it, but low-angle illumination can create complicated patterns. Some elevated places may receive long periods of light. Nearby areas may fall into shadow. A mission has to plan not only where the sun is, but what the terrain does to the sun. Communications can become geometry too. Earth visibility, local terrain, lander position, relay needs, and surface movement all matter. The Moon is close compared with Mars, but close does not mean simple. A ridge can block a line, a crater can complicate a path. A surface operation needs to know when and where signals, power, and visibility are reliable enough. Thermal conditions add another layer. Sunlit surfaces can heat. Shadowed regions can become intensely cold. Hardware has to survive transitions and extremes. A permanently shadowed region may protect ice over geologic time, but it does not make human access easy. A place can be scientifically valuable because it is hostile to change and operationally hard for the same reason. This is why saying Apollo landed on the Moon does not answer whether Artemis can operate at the South Pole. It is the same celestial body, but not the same local problem. On Earth, landing on a beach does not prove you can operate safely on an Antarctic ridge in winter. The planet is the same, the environment is not. And this is one of the strongest answers to the title. Artemis is not trying to replay the easiest memory of Apollo. It is trying to go to a region that may tell us more, provide future resources, and support longer ambitions. The price of that scientific value is operational difficulty. The South Pole turns light into a constraint. It turns terrain into a navigation problem. It turns power into a schedule. It turns communications into geometry. It turns the Moon from a familiar disk in the sky into a difficult place on the ground. Apollo proved the Moon could be reached. The South Pole asks whether humans can work where the Moon is least convenient and most interesting. The South Pole also changes how humans perceive risk. On Earth, our eyes are trained by atmosphere, scattered light, familiar shadows, and everyday scale. On the Moon, without air to soften the light, contrast can be severe. A shadow can hide depth. A bright patch can wash out detail. Distance can be hard to judge. For astronauts, perception is not cosmetic. Seeing terrain correctly affects walking, driving, landing, tool use, and emergency return. For machines, perception becomes software, sensors, maps, and lighting systems. A place that is visually dramatic is also operationally demanding. The permanently shadowed regions deserve their own moment here, because they are both the prize and the problem. These are craters and depressions near the poles, where the sun's geometry means direct sunlight has not reached the floor in billions of years. Temperatures there can drop below -160 degrees Celsius. At those temperatures, volatile compounds including water ice can survive over geological timescales. That is why they are scientifically compelling and strategically interesting. Water is heavy to launch from Earth and potentially usable for life support, fuel production, or both, but accessing those regions changes the mission requirements sharply. A crew or rover approaching a permanently shadowed area cannot rely on solar power at the site. Thermal systems have to handle extreme cold rather than the more familiar problem of rejecting heat. Lighting has to be carried or positioned artificially because the sun provides none. Navigation has to rely on maps, sensors, and pre-planned routes rather than visual landmarks that change with sun angle. Communication to Earth from inside a deep crater may require relay assets. This is not a reason to avoid the shadowed regions. It is a reason to plan for them honestly. The most scientifically valuable places at the South Pole are the ones that impose the highest operational cost. That trade-off does not resolve itself just because the destination is compelling. It has to be engineered around, and engineering around it takes time, mass, power, and verified hardware. The South Pole is also a mapping problem. Before humans trust a site, teams need terrain models, illumination studies, hazard maps, communication analysis, thermal expectations, and landing constraints. The region has been studied from orbit, but orbital knowledge has limits. The surface always has more detail than the map. Landing site selection therefore becomes a balance. Science wants access to interesting terrain and possible volatiles. Safety wants flatter ground, better lighting, reliable communications, manageable slopes, and clear abort logic. Power wants sunlight. Thermal survival may want avoidance of extreme cold. Mobility wants routes. No single site gives every advantage perfectly. That tension is not unique to the Moon, but the Moon makes it sharp because every kilogram and every hour matters. If a site is scientifically rich but operationally punishing, the mission has to decide how much risk and complexity that richness is worth. If a site is safer but less scientifically valuable, the mission may lose part of the reason for going. Apollo landing sites were chosen through their own safety and science logic. Artemis sites carry a different balance. The South Pole is attractive because it may help answer questions Apollo could not answer in the same way. That means the modern mission inherits new value and new difficulty together. Now add the demand for return visits. A site cannot only be interesting for one set of footprints. If the long-term idea is to learn how to operate, then planners need places where later missions can build on earlier ones. Routes have to be remembered, hazards have to be mapped with increasing confidence, power and communications choices have to make sense not only for a single EVA, but for a pattern of work. We can think of the South Pole as a laboratory that refuses to simplify itself. The ice question pulls us toward shadow. The power question pulls us toward light. The landing question pulls us toward flatter, safer ground. The science question pulls us toward complexity. The crew safety question asks whether all of those pulls can be balanced without turning the mission into a maze. That is why this region is not just a destination. It is a negotiation with the Moon's geometry. So when we say Artemis is going back to the Moon, we should hear a quiet correction. It is going back to a different kind of Moon than the one most people picture. Same world, different environment, different operating problem. The South Pole also affects time. Mission planners care not only where sunlight falls, but when. A route that is safe at one moment may become harder when shadows shift. A surface task that seems simple in one lighting condition may become risky in another. A power plan depends on illumination over hours and days, not on a single beautiful image. This turns operations into choreography with the environment. Crews, landers, rovers, communications and power systems have to move through windows of usability. The Moon is not changing quickly like Earth weather, but its slow geometry is still operational. Shadow can be as decisive as weather if the system depends on light, so the South Pole is not just a harder backdrop, it is a different clock, a different lighting regime, a different navigation problem, and a different balance of science and safety. That is exactly why it is worth going to, and exactly why Apollo does not make it routine. There is another layer here that is easy to miss from Earth. The South Pole does not only challenge the machines, it challenges how a crew spends attention. On a short surface mission, attention is one of the scarcest resources. Astronauts have to monitor suit health, follow timelines, handle tools, communicate with the lander and Earth, watch footing, manage dust, preserve samples, and stay aware of how much time and consumables remain. A complicated landscape does not politely wait while the crew thinks through one problem at a time. It presents several at once. That is where operations become science in motion. A sample may be valuable because of where it sits geologically, but reaching it may cost time, light, thermal margin, or crew energy. A permanently shadowed region may hold clues about water and volatile history, but entering or approaching it may require special lighting, mobility, communications, and thermal planning. The question is not just, can we get there? The question is whether the system can let humans do meaningful work there without spending so much effort surviving the site that the science collapses. Think about the difference between visiting a place and working a place. Visiting can be brief, symbolic, and tightly scripted. Working requires adaptability. It requires spare capacity. It requires tools that do not become useless when dust coats them. It requires routes that remain understandable when the sun is low. It requires a crew that can make decisions when the plan meets the terrain. The South Pole therefore becomes a test of operational maturity. A program can land, take a few images, and leave. That would be an achievement. But Artemis is aimed at something more demanding, learning whether humans can operate in the most valuable parts of the Moon, not just touch the easiest patch of ground. That is a different standard from Apollo memory. It is also the reason the difficulty is intellectually honest. So the South Pole answer is sharper than a generic statement about difficulty. Artemis is not merely returning to the Moon as an address. It is aiming at a region where light, cold, terrain, communications, power, science, and human workload all press on one another. Apollo tells us people can work on the lunar surface. The South Pole asks whether a new system can work in this particular lunar surface environment. That distinction carries us into the final problem. The problem is no longer only distance, it is convergence. Every link has to arrive together. The vehicle, the site, the suits, the maps, the power plan, the communication path, the surface timeline, and the way home. A return becomes routine only when those pieces stop being separate hopes and become one operating system. Now the answer comes into focus. Going back to the Moon is still hard because the real goal is not one return. It is repeatable return. And repeatability is not a feeling. It is not nostalgia. It is not a launch date. It is a chain that has to survive contact with reality again and again. Apollo proved humans could touch the Moon. Artemis has to prove humans can keep a path open. Those are related achievements, but they are not the same achievement. Look back at the chain we have followed. A rocket has to launch. A crew vehicle has to keep people alive. A navigation system has to guide them across deep space. A capsule has to survive lunar return re-entry. A heat shield has to sacrifice itself predictably. Parachutes and recovery have to work. Then, for landing missions, Orion has to meet a lander in lunar orbit. The docking system has to function. Astronauts have to transfer. The lander has to descend, support surface operations, and ascend again. Suits have to turn human bodies into working spacecraft. Dust has to be managed. Power and communications have to survive the South Pole environment. The crew has to return to Orion. Orion has to bring them home. Then the program has to learn from it and do it again. A single weak link can stop the chain. That does not mean the chain is doomed. It means the chain is real. And the chain has another property that matters. The links have to converge at the same time. It is not enough for a lander to be promising in one schedule, suits to be promising in another, mission operations to be ready in a third, and surface plans to be mature on paper. A crewed landing needs readiness to overlap. The hardware, software, procedures, training, safety reviews, supply chains, launch windows, and recovery plans all have to meet at one moment and hold together. This is one of the least cinematic parts of lunar return, but it may be one of the most important. Complex programs do not fail only because one part is impossible. They often struggle because many possible parts mature at different speeds. One system is ready for test, another needs redesign, a third needs more data, a fourth depends on the first three. The result can look like hesitation from the outside, when inside the program the real work is synchronization. Convergence is hard because the Moon does not care which subsystem was ready first. The crew cannot land with a half-ready suit, or depart with a half-ready ascent plan, or rely on a communication architecture that almost covers the route. The mission accepts the whole stack, or it does not fly. This is why successful tests do not end the work. Artemis II succeeded as a crewed flyby and return. That is a milestone. It also returned data, inspections, and follow-up items. The lesson is not that success secretly means failure. The lesson is that modern human spaceflight turns success into evidence, and evidence into the next set of decisions. That mindset can feel slow from the outside. We want spaceflight to move like memory. Apollo happened in black and white footage, compressed by history into a few iconic moments. But the real Apollo was also procedures, tests, factories, failures, redesigns, simulations, risk meetings, and people arguing with physics until a path held together long enough to fly. Artemis has its own version of that struggle, not because the Moon changed its mind, because the goal changed. Safer, more repeatable, more inspectable, more ambitious on the surface, more distributed across systems, more tied to a future where the Moon is not simply visited, but operated around and on. So the serious answer is not that NASA forgot how to go. It is not that Apollo was fake. It is not that one hidden flaw explains everything. The serious answer is that lunar access was never turned into routine infrastructure. It was achieved, celebrated, and stopped. Now the route has to be rebuilt through a different architecture and a different standard of proof. And maybe the strangest part is this. The ultimate sign of success would be boredom. Not because the Moon is boring. It never will be. But because a mature transportation system makes individual operations less miraculous. Planes crossing oceans are still astonishing in a physical sense. We rarely feel that because the system became reliable enough to fade into the background. The Moon is nowhere near that state. Every mission still carries the sharp edge of test flight. Every surface plan still touches unsolved operational details. Every new system has to earn confidence. Apollo gave humanity the first answer. Yes, we can reach the Moon. Artemis is trying to answer the harder follow-up. Can we make the path back dependable enough to use again? Until that answer is yes across the whole chain, going back will remain hard. Not because the Moon is unreachable, but because reaching it once was never the same as making it routine. The word routine can sound like a betrayal of wonder. It is not. Routine is what lets wonder become usable. The first crossing of an ocean is heroic. A regular crossing is civilization. The first lunar landing was heroic. A repeatable lunar route would be something different. Less cinematic in any single moment, but more transformative over time. That is the real threshold Artemis is approaching. Not the threshold between impossible and possible. Apollo crossed that. The threshold between possible and dependable is harder to see, harder to film, and harder to declare. But for human spaceflight, it may be the more important one. Repeatability also means failure has to become survivable in the programmatic sense. Not every anomaly can threaten the existence of the entire effort. A mature system can find a problem, understand it, fix it, and fly again without relearning the whole mission from zero. That is a high bar for lunar spaceflight because each mission is expensive, rare, and tightly coupled. This is why cadence matters. The more often a system flies, the more data it gathers, the more teams practice, and the more the hidden machinery of operations improves. Long gaps make every mission heavier. They increase the burden of remembering, retraining, revalidating, and reassembling confidence. There is a specific kind of institutional knowledge that only cadence can build, and it is different from the knowledge in a design document. A launch team that has processed the same vehicle 10 times knows things that cannot be written down completely, which step tends to run long, which interface has a history of minor surprises, which inspection is worth extra attention even when the formal checklist says proceed. That knowledge is built through repetition and erodes through absence. This is one of the underappreciated costs of the gap between Apollo and Artemis. It was not only that hardware had to be redesigned, teams had to relearn how to do things that had once been practiced enough to feel routine. Some of that relearning happened through new flight experience. Some happened through simulation and analysis. Some is still happening. The gap was not only a technical problem, it was an institutional one. A program that flies regularly does not start from zero after an anomaly. It has the context to understand the anomaly faster, the bench strength to investigate it in parallel with other work, and the near-term flight schedule that creates pressure to resolve it rather than defer it. A program that flies rarely has fewer of those advantages. Each mission carries more weight, which means each anomaly weighs more, which means recovery takes longer. Cadence is therefore not only an operational goal, it is part of what makes the system mature. A repeatable lunar route would require not just vehicles, but rhythm, processing rhythm, training rhythm, manufacturing rhythm, inspection rhythm, surface operations rhythm. Lessons returning from one mission would have to feed the next before the organization forgets them or the hardware changes too much. But rhythm is difficult when each mission depends on so many different clocks. One clock belongs to launch vehicle processing, one belongs to Orion refurbishment and inspection, one belongs to lander development, one belongs to suit certification, one belongs to ground systems, recovery forces, range availability, mission rules, and crew training. The Moon adds its own clock through lighting, launch windows, orbital geometry, and landing site conditions. So repeatability is not merely the ability to do the same thing again someday. It is the ability to make all of those clocks line up often enough that the system keeps its memory. If the gaps are too long, the route remains fragile. If the cadence becomes real, the route starts to harden. People learn, suppliers learn, procedures improve. The mission stops being a once-in-a-generation performance and starts becoming an operating capability. That may sound mundane compared with the poetry of footprints, but it is the heart of becoming spacefaring in any practical sense. A civilization does not become a seafaring civilization by launching one perfect ship. It becomes seafaring by building ships, ports, charts, crews, repair yards, laws, rescue practices, and habits that survive beyond the first voyage. The Moon asks for the same kind of transformation in a harsher environment. Apollo was the first voyage that proved the ocean could be crossed. Artemis is an attempt to build something closer to a route, and routes are harder than flags. The final mental model is this: spaceflight progress is not a video game level unlocked forever. It is closer to a living bridge. It has to be maintained. People have to know how it was built. Materials have to be inspected. Loads have to be understood. If the bridge is abandoned for decades, the fact that it once carried traffic does not mean it can carry traffic tomorrow. Apollo built and crossed a bridge to the Moon. Then the traffic stopped. Artemis is not merely walking back onto the old bridge. It is building a new one, with new lanes, new standards, new materials, new destinations, and new expectations for how often it should be crossed. That is why the answer is both humbling and hopeful. Humbling because no past triumph exempts us from present physics. Hopeful because the difficulty is understandable. It is not magic, it is not mystery for mystery's sake. It is the work of turning a once-in-history achievement into a system strong enough to use again. And that is the right place to land this point. Repeatability changes the meaning of success. A single success can be heroic. A repeated success becomes capability. The difference between those two things is the full distance between Apollo and what Artemis is trying to prove. The goal keeps becoming more honest. Early exploration can be satisfied by arrival. Mature exploration has to ask what arrival is for. If the goal is only a flag, the system can be narrow. If the goal is science, return visits, and preparation for what comes after, the system has to be broad. That broader goal makes the Moon harder in the short term. It is also the reason the difficulty is worth the work. So when we look up at the Moon, the contradiction is still there. It is close enough to see with the naked eye. It is familiar enough to feel almost domestic. It has human footprints on it. It has flags, instruments, rover tracks, descent stages, and the memory of voices speaking from another world, and still, it is not routine. Apollo was not small. Apollo was not fake. Apollo was not a trick humanity forgot. Apollo was a proof of possibility, achieved through a concentrated sprint and a specific machine built for a specific mission. It showed that humans could reach the moon, land, work briefly, lift off, rendezvous and return, but Apollo did not leave behind a standing lunar route. It did not preserve a living industrial ecosystem. It did not solve South Pole operations. It did not certify modern landers, modern suits, modern docking interfaces, or a repeatable campaign of surface missions. Artemis II now gives us a strong modern proof of one layer. A crewed Orion went around the moon and came home safely. That matters. But a flyby is not a landing, and a landing is not surface operations, and surface operations are not a repeatable system. So the sentence we started with is still true, and now it is more precise. We already went to the moon, but we did not make the moon routine. Think of two maps. The first has one bright line from Earth to the moon and back. That is the map memory keeps from Apollo. It is true and it is beautiful. The second is covered in smaller markings, test points, inspection gates, docking loads, suit clearances, dust paths, lighting windows, power margins, communication shadows, ascent timing, recovery zones, and lessons still waiting for the next flight. That is the map Artemis has to fly. We need both maps. Without the first, the dream has no proof. Without the second, the proof has no future. Apollo proved we could touch the moon. Artemis has to prove we can keep a path open, and that path, not the distance alone, is why going back is still so hard.